What if everything we knew about black holes was wrong? For decades, black holes have been portrayed as the ultimate cosmic monsters, massive, invisible, and endlessly hungry. They devour stars, bend time, and nothing, absolutely nothing, can escape them, not even light. But there's one problem. Black holes break physics. The moment you hit the center of a black hole, what's called a singularity, our laws of science simply stop working. Gravity becomes infinite. Space and time collapse into a single point. It's like running a computer program and suddenly getting the error does not compute. That's where a strange and fascinating idea called the Gravastar comes in. A gravastar, short for gravitational vacuum star, is a hypothetical object that looks a lot like a black hole from the outside, but is something completely different on the inside. It was proposed in the early 2000s by physicist Powell Mazer and astrophysicist Emil Matola. These two weren't trying to stir up science fiction. They were looking for a solution, one that could remove the singularity problem at the heart of black holes. So what is a gravastar, really? Imagine you've got a massive star. It burns for billions of years, and then like all giant stars, it runs out of fuel. It collapses under its own gravity. Normally, this leads to a black hole, right? But what if instead of a singularity, the collapse stops just short of that point? According to Mazur and Matola, that's when something incredible could happen, the formation of a gravastar. At its core, a gravastar doesn't contain matter as we know it. Instead, it's filled with something called vacuum energy, a bizarre form of energy that exerts a kind of negative pressure. Vacuum energy is not just theoretical. It's been observed in quantum physics and is even linked to the mysterious dark energy that's accelerating the universe. In a gravastar, this vacuum energy pushes outward, while gravity pulls inward. The two forces cancel each other out. The result? A perfectly stable sphere with no singularity, no infinite gravity, just a weird quantum bubble holding everything together. On the outside, though, a gravastar looks almost identical to a black hole. It's incredibly dense. Light bends around it. And from far away, not even the most powerful telescope can tell the difference. But there's a twist. Gravastars don't have an event horizon. That's the point of no return in a black hole, where light and matter vanish forever. In a gravastar, because there's no singularity inside, some theories suggest that information energy might not be lost. They could bounce back, or even leak out slowly over time. This brings us to one of the biggest mysteries in physics, the black hole information paradox. According to quantum mechanics, information can never be destroyed. But black holes seem to do exactly that. They swallow information with no trace. Stephen Hawking himself struggled with this paradox for years. Gravastars might offer a way out. If they exist, they could preserve information in ways black holes can't, restoring balance between general relativity and quantum theory. But are gravastars just a thought experiment, or could they be real? Scientists are trying to find out. Gravitational wave observatories like LIGO and Virgo are now listening to the universe in ways we never could before. When two massive objects collide, like black holes or neutron stars, they send ripples through spacetime. These ripples carry signatures, clues, like a fingerprint of what created them. Some physicists believe that if we ever detect small echoes or irregularities in these waves, it might be a sign we're not hearing black holes, but gravastars. There was even a paper in 2016 that claimed to find such echoes in the LIGO data, but it's still under debate. So far, no one has definitively proven gravastars exist, but no one has ruled them out either. Another theory comes from quantum gravity research. According to some models, space-time itself might have a quantum structure, like pixels in a digital image. If true, then objects like gravastars could be part of that structure, replacing black holes in extreme environments. They could be made from exotic forms of matter or even built from loops of space-time. And here's a fun twist. If gravastars exist, they could explain strange cosmic phenomena that black holes can't, like fast radio bursts, sudden explosions of energy from deep space, or objects that seem to have the mass of a black hole but don't behave like one. In a way, gravastars could be nature's hidden cheat code, solving some of the biggest contradictions in physics. They preserve Einstein's equations but dodge the deadly singularity. They respect quantum rules but still bend space and time. and they force us to ask what's really out there. Maybe in the shadows of the universe, some of those so-called black holes aren't black holes at all. Maybe they're gravastars quietly holding their secrets, waiting for science to catch up. And as our telescopes get sharper and our gravitational wave detectors more precise, we might just get the answer. Until then, gravastars remain one of the most fascinating what-ifs in modern astrophysics, a cosmic mystery sitting right at the edge of known science.